Hi everybody, welcome back to the channel. In this video we're going to take a look at finding derivatives of exponential functions. And we're not going to necessarily look at every single detail of every proof, but exponential functions behave pretty nicely in general. And to start out, we're going to look at two different kinds of exponential functions. We're going to look at what happens when we have a base of just kind of a general number b, and then we're also going to look at a very specific exponential function that you've probably seen before, but the letter E, which maybe you remember, but E is a decimal. It's actually an irrational number, kind of like pi. And as a decimal, E is something like 2.71, so on and so forth, keeps on going. And you may have used E back when you talked about finances in a past class, or when you talked about exponential and logarithmic functions. So b to the x and e to the x, kind of two different cases, and we're going to look at what happens when we take the derivative of both of those. All right, so let's start out by just looking at b to the x, and then we're going to kind of figure out why e is such a special number and kind of look at where that comes from. So let's go back to the limit definition of a derivative. We're developing rules about derivatives, but in order to kind of have those rules in the first place, almost every time we're going to go back to this limit definition and build up these rules so that we don't have to go back to the limit definition after we've proven these rules every single time. So let's start with something like b to the x. And remember, the limit definition says f of x plus h. So we're going to go ahead and use b to the x plus h, and then minus f of x, so minus b to the x, and all over h. And remember, the idea here is that we're not allowed to plug in 0 here, otherwise we would get 0 over 0. So what we've been doing all along is saying, okay, how can we simplify this and kind of work with this to be able to kind of get to a point where we can plug in 0 for h. Now, we can't factor like we could have with rational functions. We can't be able to combine a bunch of stuff together and kind of see what happens, but we can use some of the rules that we know from our past. Specifically, I want to kind of focus on this b raised to the x plus h part, and hopefully one rule that you remember from your past is the rule that says, let's not put equals there for a second. There's a rule from your past with exponentials, or I should say with exponents, that says that x to the n power times x to the m power, if you remember what you do with those, you would add those exponents together. That would become something like x to the n plus m power. And so we actually have something that looks like the right side of that equation over here with b to the x plus h. In other words, you can go ahead and one thing you could do, maybe the only thing you can do at this point, is to split this up as b to the x times b to the h minus b to the x all over h, and split it up like that. Now at this point, you can go ahead and factor out a b to the x on the top. So factor out a b to the x, and what you're left with is b to the h minus 1, and then an h on the bottom still. And what we could look at is kind of this part right here that has a b to the h minus 1 all over h. And remember, b is a constant. It's just an arbitrary constant right now. But what ends up being really interesting is that if you look at different values of b, go ahead and just kind of play around with different values. I would recommend, by the way, h, remember, is getting close to 0. So you almost could make yourself a little table that says try different values of b, and then use a really small value of h, and see what happens to the part that's circled. This is b to the h minus 1 all over h. Let's go ahead and use something like h as 0.001. And you could try something like what happens when b is 2, when b is 3, and like test out different things for b. What's really interesting is that if you use b as 2.71 something something something, and then use h as 0.01, what happens when you find the value of b raised to the h minus 1 all over h? When you go ahead and look at that and you use a value of b as 2.71 something and h as a really, really small value, what you end up getting is that basically is equal to 1. Okay, and so really the part in the circle over here ends up being 1 when you've chosen the value of b to be 2.71 ... Well, you may remember that 2.71 is actually that value of e. So if you actually use e as your base instead of kind of a generic b, what you end up getting is this b to the h minus 1 over h ends up giving you 1. And then since b is being replaced by an e, you end up just getting e to the x. And it ends up giving us a really interesting result. Here's what this ends up giving us. Really what we're saying here is that if your original function is f of x equals e to the x, so don't use a generic b, use that specific number of e, this number of e is a really special number where it's the number that makes the b to the h minus 1 all over h gives you 1, so that its derivative actually ends up giving you just exactly e to the x. So this is a really special function, and that's why e is a really special number, especially in calculus. Okay, so before this, if I were to ask you what irrational numbers do you know, you would probably say, well, I know pi, I have a lot more familiarity with that. E is irrational, but I haven't dealt with that a whole lot. Really, once you get to calculus and higher, e becomes really important, and probably, you could argue this, but probably more important than pi from the perspective of irrational numbers. Because what we're saying here is that here is a function that is its own derivative. That does not happen a lot. And it actually makes things really nice when you're talking about calculating derivatives, because then if I said something like f of x is equal to 5e to the x, what's the derivative of 5e to the x? Well, again, when you have a constant multiplier out front, it just stays out front. So since e to the x is its own derivative, 5e to the x is also its own derivative. So anytime you have a function that has an e to the x, this actually behaves really, really nicely. This is probably one of those that you want to put on your derivative rules formula, but honestly, you probably won't need to refer back to this one a whole lot. This is actually really nice. I have students all the time who struggle with knowing derivatives and who have to go back to their derivative formula sheets all the time, but when they see an e to the x, they start celebrating because they're like, great, I know that one. I don't struggle with that one, because it is its own derivative, which is great. Now, that's because e is a really special number, and that is not always the case for just some generic b to the x, okay? But the function b to the x behaves pretty similarly. If we had the original function b to the x is almost its own derivative. It's not exactly its own derivative, but it's almost its own derivative. And so there is a b to the x part in there, but when we're taking the derivative of an exponential function that doesn't just have an e as the base, we actually have to have an extra constant on the end. And that specific constant that we have on the end every time is the natural log of b. Remember, b is not a variable here, b is a constant. And whatever our base is there, we need an extra natural log of b. So the one on the bottom here with b to the x is true kind of for a generic for any exponential function. E to the x is a really specific exponential function because the value of e is really specific, but it's one that shows up enough that it's worth kind of mentioning these two as being separate, because we do see e to the x show up all the time in the natural sciences. So you might ask yourself, hey, if this formula right here for the derivative is supposed to work every single time, like, do we need two separate formulas? I mean, think about it like this. The formula for e also satisfies this b to the x times the natural log of b. We would be saying that f prime, if you had f of x as e to the x, f prime of x, if you wanted to use the formula down here that talks about just a generic b, that would be e to the x times the natural log of e. And so you say, well, okay, why don't we use that one? Well, we are. But what's the natural log of e? That's just 1. Okay, so really we end up just getting just e to the x times 1, which is why we still just get e to the x up here as its own derivative. And so, again, e is such a common exponential function that we're going to include these two separately. But whenever you see a function that looks like b to the x, you need to know how to deal with that one as well. So let's take a look at one last example. Again, exponential functions is going to be pretty quick here, but let's look at one example with this. So let's say you have a function that looks like f of x equals 3 to the x. And just for the sake of some variety here, I'll throw in plus 4x to the negative 7 as well. Okay, or a fun one there would be to kind of talk about something like f of x equals 2 to the x plus x squared, where you just got to be really careful about what your base is and what your exponent is. We could look at both of these. So the first one up here, the derivative, this is like your b to the x. It's a 3 to the x here. So the derivative of that first part is a 3 to the x. Remember, that's almost its own derivative, but then we need an extra natural log of 3. And then the second part is not an exponential, but I just want to make sure that we throw in some variety here. That's actually a power rule there, where you could write the 4 out in front, and then the negative 7 is going to come down, so you're going to get a negative 28. And then x to the, careful here, negative 7, and you drop by a power of 1, you go down. This is to the negative 8th power, not negative 6, negative 8th. Okay, so again, we can throw in exponentials with power rule problems, and we're going to see different functions that combine all these things together all the time anyways. So for the second one, f prime of x is equal to 2 raised to the x times the natural log of 2, and then plus 2x from the power rule. Okay, so this is the derivative of exponential functions. Hope you've enjoyed. Good luck practicing.